In this episode, we shift from the idea of cryptography as a magical protective wrapper to cryptography as a set of engineering choices that can either reduce risk or accidentally create new holes. Beginners often assume that if they pick something with a crypto-sounding name, everything becomes secure automatically, but real security depends on choosing algorithms that are still trusted, picking parameters that resist modern attacks, and configuring everything so the protection actually applies the way you think it does. A surprising number of breaches and data exposures happen not because someone broke the math, but because the math was outdated, the settings were weak, or the system was misconfigured in a way that silently removed the protection. The goal today is to help you recognize what safe choices look like at a high level, why certain crypto gets deprecated, what weak parameters really mean in practice, and how configuration pitfalls show up in the real world. By the end, you should be able to hear a crypto-related decision and immediately ask the right safety questions, even if you are not implementing anything yourself. A good starting point is the idea of deprecation, because crypto does not stay equally safe forever. An algorithm can be widely trusted for years, and then new research, faster computers, or clever attack techniques reduce its safety margin until it becomes risky to use. Deprecation is the process of the security community and vendors gradually moving away from an option because it is no longer a safe default. Sometimes the algorithm is truly broken, meaning there is a practical method to defeat it, but more often it becomes weak in a more gradual way, where it still works, but no longer offers a comfortable buffer against attackers. This is why cryptography is often described as having a shelf life, even though the math itself has not changed. The mistake beginners make is treating old crypto like an old lock that is still fine as long as it is not obviously broken, when the real issue is that attackers improve continuously and your defenses must maintain a comfortable distance ahead of them. It also helps to distinguish between an algorithm being deprecated and an implementation being flawed, because these are different failure modes. If an algorithm is deprecated, even a perfect implementation is now a risky choice because the underlying design no longer offers sufficient protection. If an implementation is flawed, a strong algorithm can still fail because the code mishandles keys, leaks secrets through timing, or uses insecure randomness. In this lesson, we focus mostly on selection and configuration, but it is important to remember that cryptography is a stack. You have the algorithm, the mode of operation, the key management, the randomness, and the protocol rules that explain how everything is combined. A weak link anywhere can collapse the whole structure. That is why security teams talk about approved sets of algorithms and settings, because they are trying to control not just one layer, but the overall system behavior. Weak parameters are one of the easiest ways to accidentally lower the security of otherwise respectable cryptography. Parameters include things like key length, the curve or group used in key exchange, the number of iterations in a password-derived key, and the chosen mode for how encryption is applied to data. The reason parameters matter is that cryptography often offers a dial you can turn between performance and security, and turning it too far towards speed can make attacks feasible. A short key reduces the search space and makes brute force more realistic. A weak group in key exchange can allow attackers to recover secrets with less effort than expected. Too few iterations in a password-based process makes guessing passwords far faster, which matters because humans choose predictable passwords. The beginner takeaway is that crypto is not just a brand name. It is a set of choices, and choosing the minimum option or the fastest option can quietly undercut the protection. One common pitfall is using encryption without integrity, which sounds technical but is easy to understand. Encryption is meant to hide information, while integrity is meant to detect unauthorized changes. If you encrypt data but do not include a strong integrity check, an attacker might not be able to read the content directly, but they may be able to alter it in a way that causes predictable changes when the system decrypts it. This can lead to subtle vulnerabilities where the data looks protected, but the system can be tricked into accepting modified ciphertext as legitimate. Modern safe approaches tend to combine confidentiality and integrity in a way that is designed to work together, because treating them as separate add-ons often leads to mistakes. A helpful mental model is to think of a sealed envelope that is also tamper-evident. If you only seal the envelope but do not make tampering visible, someone can still manipulate the contents while leaving you unsure whether it was altered. Another major category of pitfalls involves randomness, because cryptography relies on unpredictable values for keys, nonces, and other secret numbers. If the randomness is weak, the resulting keys or values may be guessable, which can collapse security even if everything else is configured correctly. Weak randomness can come from poor sources of entropy, reuse of values that were meant to be unique, or predictable patterns introduced by flawed logic. A classic beginner misunderstanding is to think randomness is just calling a function that returns a number, when in security the quality of unpredictability matters deeply. The consequence is that two systems can both claim to use the same algorithm and key size, but one is secure and one is not, simply because one generated the key from strong randomness and the other did not. When you are evaluating crypto choices, it is not enough to ask what algorithm is used. You also need to ask how keys and unique values are generated. Configuration pitfalls also show up when people choose defaults without understanding what they mean, especially when the defaults prioritize compatibility. Many security protocols offer negotiation, meaning two systems agree on a mutually supported set of algorithms and parameters. This is convenient, but it also creates a risk. If the allowed list includes weak choices for legacy reasons, an attacker may be able to force a downgrade to the weaker choice. Even without active attack, a system might settle on a weaker option simply because that option is widely supported and the operator never restricted the configuration to safe settings. The deeper issue is that security often requires explicit disabling of old choices, because keeping them available for compatibility means they remain part of the attack surface. Safe crypto selection, therefore, includes not only picking a good option, but also removing unsafe options from the menu so they cannot be selected accidentally or maliciously. A related beginner trap is misunderstanding what it means for cryptography to be present versus being correctly applied. You can have encryption enabled, but still leak sensitive information through metadata, logs, error messages, or backup copies that were not included in the protected scope. You can have strong encryption on stored data, but leave a copy in a cache or temporary file that is unencrypted. You can have secure communication, but allow plaintext fallback for troubleshooting and forget to turn it off. These are not failures of cryptographic math. They are failures of boundary definition and configuration discipline. This is why security professionals often say that cryptography is easy to add and hard to get right, because the hard part is making sure the protection covers the entire path the data travels and the entire lifetime the data exists. Another major pitfall is mismatched goals, where the chosen cryptographic method does not match the security need. For example, people sometimes reach for encryption when the real requirement is authenticity, meaning you need to be sure who created a message and that it was not changed. Or they might use a checksum-like approach when they really need a cryptographic integrity check that attackers cannot forge. Sometimes the goal is confidentiality for data at rest, but the chosen design exposes keys widely, making confidentiality brittle. The safe selection mindset begins with clearly stating what you are trying to achieve: confidentiality, integrity, authenticity, non-repudiation, or a combination. Once the goal is clear, you can evaluate whether the chosen crypto mechanism actually provides that property in the way the system is used. Beginners become much safer when they stop asking, "What crypto are we using?" and start asking, "What security property do we need? And does this design actually deliver it?" Password-related cryptography deserves special attention because it is where weak parameters and misconfiguration commonly collide. Humans choose passwords that are guessable, and attackers can test guesses at enormous scale, so systems must compensate by making guessing expensive. That cost is created by key-stretching settings, such as iteration counts and memory requirements, which are parameters that must be chosen carefully. If those settings are too low, attackers can guess quickly. If they are too high, legitimate systems may become slow or unstable. Another pitfall is using the same derived value in multiple places or failing to use unique salts, which are random values that prevent two identical passwords from producing identical results. The beginner lesson is that password security is not just about user behavior. It is also about the cryptographic settings that decide whether guessing is cheap or painful for an attacker. Deprecation can also happen at the protocol level, where the problem is not a single algorithm but the way components are combined. A protocol might use a strong cipher but have a handshake that allows downgrade tricks, Or it might use a safe key exchange but fail to bind identity properly, allowing man-in-the-middle positioning. Protocol failures can also involve weak defaults that were acceptable decades ago but are now dangerous, like allowing short keys, allowing outdated integrity checks, or permitting insecure renegotiation behaviors. This is why security professionals prefer well-studied modern protocol versions and actively disable older ones, even if older ones still appear to work. For you as a beginner, the key habit is to treat protocol versions as meaningful security choices, not just compatibility checkboxes. When someone says they support a range of versions for convenience, your alarm bell should go off, and you should ask how they prevent the weak end of that range from being used. A subtle but important configuration pitfall is believing that compliance with a checklist automatically means safety. Checklists can help, but they can also encourage a shallow approach where people enable a feature and move on without validating what the system actually negotiated or enforced. A safe approach includes verification, like ensuring that weak algorithms are truly disabled, that keys are the intended size, and that the system is not silently falling back to insecure modes. Even without touching tools, you can understand the concept of validation as asking, how do we know the secure setting is active during real operation, not just written in a configuration file? Many crypto failures are discovered only after someone checks what was actually happening on the wire or in the service behavior and realizes the intended security setting was never truly in effect. The mindset shift is to treat cryptography as an outcome you confirm, not a feature you assume. To bring it all together, choosing crypto safely means building a conservative, modern posture that avoids deprecated options, avoids weak parameters, and avoids configurations that allow negotiation into unsafe territory. Deprecation matters because attackers and research move forward, and yesterday's safe option can become today's liability. Parameters matter because they control the real strength of the system, and weak settings can make attacks practical even when the algorithm name sounds impressive. Configuration pitfalls matter because cryptography is often defeated through defaults, fallbacks, and boundary mistakes, not through heroic mathematical breakthroughs. If you carry one lesson forward, let it be this. Secure cryptography is less about finding the fanciest option and more about choosing well-supported modern options, using strong parameters, disabling weak alternatives, and verifying that the system truly enforces what you think it enforces.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.